string. We are going to solve the one-dimensional wave equation for a string, which will move step by step through the boundary conditions to derive the exact displacement of y of x, t. The scenario. The waveforms represent the integer value of n or eigenvalues that will encounter our solution later. The lambda 1 corresponds to n equal to 1 and lambda 2 n equal to 2 and so on. Here are numerical parameters. The string exists between x is equal to 0 and x is equal to L at the same time t equal to 0. We displace the string into parabolic function defined as y equal to k Lx minus x square. The motion is governed by partial differential equation on the left. The second partial differential with respect to time at a square, the times second partial differential equation x. Our objective is to PDE for y. These are the boundary conditions. Defining the conditions, we have the mathematical constraints to apply. Boundary 1 at x is equal to 0, y is always 0. Boundary 2 x is equal to 1 for L, y is always 0. The partial derivative del by y by t equal to 0. The initial shape at t equal to 0, y our function k Lx minus x square. We assume the separable solution yt equals c1 cos px plus c2 sin px multiplied by c3 cos pat plus c4 sin pat. First, substitute x is equal to 0 into the equation. Sin 0 is 0 and cos 0 is 1. This leaves us with c1 multiplied by 1 for the result equal to 0. c1 must be 0. This removes the cosine term from the spatial part. Then substitute x is equal to L or 1 into the remaining sine term. This gives us c2 sin pl is equal to 0. Since c2 cannot be 0, the sin pl must be 0. Mathematically speaking, p would be equal to n pi by n. Now apply the time derivative condition. For something with respect to t, terms are cosine terms into sine terms and sine terms into cosine terms. T equal to 0 and the sine component vanishes naturally. However, the cosine component becomes 1. For the velocity to be 0, the coefficient attached to the cosine, which is c4, must be 0. So c4 equal to 0. We combine the surveying constant c2 and c3 into a single constant bn. Because the wave equation is linear and sum is all over the place. This yields yx, t, bn sin n pi by l and cos n pi at by l. The initial displacement. Finally, we determine the bn using the initial shape at t equal to 0. The cosine terms become 1. This leaves us with Fourier sine series equal to the parabolic function bn sin k Lx minus x square equal to bn to isolate the value of bn. Now we solve the integral. We solve this integral 0 to L k Lx minus x square sin dx. And while integrating, for even n, it becomes 0, and for odd n, the terms add up. Bn is equal to 8k L square by n cube by y cube for odd n. This is the final displacement solution.